identify or differentiate between the two electrons in the same room there. And Wolfgang Pauli came up with this principle, and it's that actually in addition to the quantum theory, and Schrodinger's equation only calculate the number of rooms in there. Or say, why can't we put 3 electrons in there? Well, when you have 3 electrons in each room, you're going to have problems there. So Wolfgang Pauli says, well, let's make sure that we set the ground rules there. We can only have 2 electrons in the in each particular orbital. And if you have 1, we don't really care which direction it spins. By convention, it's opposite the counterclockwise. Okay. But if you have 2 of them, 2 electrons in there, they must spin on the opposite direction, right? So the maximum number of electrons that we can accommodate equals to 2 times n squared. I just raised the board there. Say the total number of orbitals available equals to n squared. And if each room can accommodate 2 electrons, then 2 times n squared will give you the total number of electrons. So on the first level, n equals 1, you can only have 2 electrons. That's why we have helium, we have hydrogen, we have helium in the first period. There are only 2 elements in the first period because there is only 1 room on that level. You can only accommodate up to 2 electrons in there. When n equals to 2, you can have up to 8 electrons. 2 times n, 2 to the second power is 4. The 2 times 4 is 8. So the total number of electrons that we can accommodate in each main energy level equals to 2n squared. This is the equation, this is the relationship I need you to memorize. And if you look at the practice exam for exam number 3, you will see questions there. When n equals 5, how many electrons can we have? Well, 5 to the second power is 25. 2 times 25, 50. N equals to 7, 98, and so on and so forth. So you need to know this relationship. Okay, so again, the electron distribution in atoms there, shell number n equals 1, 2, and 3. While subshells, we can have S, S and P, S, P, and D. Okay, number of orbitals there, total number of orbitals versus total number of electrons there. So the capacity, total electron capacity would be 2 times n to the second power. Okay, so that's something that that relationship is something that we want you to remember. Now the correlation about the n value and the periodic table is that element in period 1, their electrons are on n equals to 1. So when n equals to 1 refers to the first period. N equals to 2 refers to the second period. N equals to 3 refers to the third period. Okay. Now, if you have a particular element, the electron actually goes to n equals to 2. That means n equals 1 has already been filled. If the electron actually goes to n equals to 3 in the third period, that means the first 2 levels are already filled. So you're like running a hotel. You are the manager of the hotel, and you want each of the room be occupied before on each level before you assign the gas to the rooms in a higher level. So n equals to 1, you have 1 room, you can put 2 people in there. When the third person coming in, well, that third person goes to the second level. Okay. In the second level, n equals to 2, we can accommodate up to 8 electrons. When you have the 9th person coming in, well, the 9th person will have to go to the third level, and so on and so forth. Okay. So the correlation there is that n equals to 1 represents period 1, n equals 2, period 2. Remember that group number has something to do with the charges, the elements, the atoms of those elements are there. For main group elements in metal, group number equals to the number of charge. Okay, so what we're trying to do here is that after the introduction of the quantum theory, after understanding the quantum numbers of the electron distributions there, we're trying to put everything in use. When we look at the periodic table, how do we re-understand, if you will, the periodic table? Why are we arranging the elements in this way? Well, there's a reason behind that. Okay, so the correlation is very important. Now, we try to separate the periodic table into what we call S, P, D, F blocks. And this is something that I want you to have a mental picture of. In giving you a periodic table, you would know the yellow region, the first 2 columns, plus 1 on the upper right corner. That's what we call the S block. We'll give you a reason why we call it S block in just a little bit. Okay, this particular region in green color, we call it P block. Okay, the lighter blue color, we call it D block. Then the darker blue color, we call it F block. And according to this SPDF block destination, we would categorize element as S block element, S block element, D block element, P block element. And one thing you notice there is that the S block element, they're mostly metal elements, including hydrogen and helium, which are the two non-metal elements in there. But everything else is main group elements, and it's a main group of metal elements there. Okay. The P block, though, the green section, has main group metal elements in there. Aluminum is in there, and mainly it's the non-metal elements. D refers to the transition metal, and F also refers to the transition. So S, P, D, F, and those are how when we're trying to dissect the periodic table, these are the different sections. And the reason that we call them S block is because when we get into the topic of valence electrons, these elements will have at least one valence electron occupying the S orbital. Now we know S orbital can only accommodate 2 electrons. So when you have the third electron will have to go to the P orbital. So in this section, you have at least 1 electron. You can have up to 6 electrons. You have at least 1 electron. After the S orbital is filled, you have at least 1 electron occupying the P orbital, so we call it P orbital. In this section, as you guessed, S and P are filled. You have at least 1 electron occupying the D orbital, so we call it D block. You have at least 1 electron occupying the F orbital, we call it F block. Okay, so that's how we designate SPDF block, and this is something that I need you to memorize and have a mental picture of this particular destination. In the practice exam and in the homework assignments and the upcoming exam for the third exam there, I will give you a particular element. I will ask you a list of elements, if you will, a list of 4 or 5 different elements there. I'll ask you which one is a D block element. You need to know where the D block is. Okay, and so this is a diagram actually in your textbook. I'm giving you slightly different color coding there. The first 2 columns are the S block, and these, the non-metal section on the far right side of the periodic table, and including some main group elements, metal elements there. This is the P block there. And as I said, these little things there, and you see there, 3s1, 3s2, those are what we call the valence electron configuration. And we are going to get into that topic in just a little bit. And the reason that we call these S block is because you have at least 1 electron occupying the outermost orbital there, and that orbital is the S orbital. Okay? And then here you start to see 1 electron on the P orbital, 2 electrons on the P orbital, 3, 4, 5, all the way to 6. Total number of electrons that we have, 6 plus 2, we have 8 electrons in here. Okay, so this is what we're looking at, and the periodic table there, SPDF block, and this is something that we want you to remember and have a mental picture of that destination there. So electron assignment there, when you fill the different orbitals there, now that we know quantum numbers basically governs how the electrons are being distributed, and